Now, there's actually a more general way to think about force too, and there are a couple different stages. So another way to look at it, we have to introduce a new math concept, and it's called the dot product. Because when you multiply force and displacement, they're both vectors. Okay, so how do I take a vector, say vector A, and multiply it to a new vector B? Okay, so you can recall from earlier, if we had these two vectors, say a vector is some x component in the x direction and some y component in the j direction, and the b vector has an x component and y component as well. Okay, all we ever did with this was adding and subtracting, right? If we added these vectors, we simply added like components. So ax and bx, and then ay, by. Okay, and then if we subtracted them, same kind of idea. But we never talked about multiplication. Now there's actually two forms of vector multiplication. We're going to do the first one, which is the dot product, and the other one we'll get to in a later unit. Okay, so how do we calculate a dot product? So let's use the same two vector distinctions, ax, ay, and bx, by. So calculating the dot product is actually fairly easy. What you're going to do is multiply like components together. Okay, and then add those products. Now you'll notice that we've lost all I hat and j hat notations. Okay, that's one of the things that's unique about a dot product. Okay, because sometimes instead of dot product, you actually hear this called a scalar product. It actually removes the vector nature. Okay, so let me give you two quick vectors. We'll say vector A is, say, 3 I hat and 2 j hat, and B vector is, say, 1 I hat and 4 j hat. Okay, then the dot product between these will be the two x components multiplied, so 3 times 1, plus the two y components multiplied, 2 times 4, so 3 plus 8, so the dot product would be 11. Okay. Now, what's unique about the dot product is it's a way to kind of mathematically pull out the parallel nature of vectors. So if we had, different vectors now, if I had a vector A sitting like this, and a vector B over here, so two vectors A and B separated by some angle, okay, what the dot product does is it pulls out the components of these that are parallel to each other. So what they call this in math is actually called a projection. It's like looking at the shadow of vector A that's produced on vector B. Okay? And then scaling up the vector based on that. Okay? So it's a projection. And when you look at something like work, for example, where the force that we want to apply, and we look at the parallel component of that force, well, the dot product is a very good way to do that, because the dot product pulls out the component of the force that is parallel to the displacement. Okay, so another way to do this another way to find the dot product, okay, you can actually take the magnitudes of the two vectors, multiply those together, and then multiply that by the cosine of the angle, where the angle is measured between the two vectors. Okay? And that's a good formula to use if we need to figure out, well, what's the angle between them? Right? So let's use the vectors we did in our first example. Okay, so vector A was components 3 and 2. Vector B was 1 and 4. Now we already found out that the full dot product of this was 11. Now what if I wanted to know the angle between them? Well, you could graph them, because graphing a vector is pretty easy. A vector is 3 units on the x-axis, 2 units on the y. Okay, so this line represents vector A. Vector B is 1 unit on the x and 4 units on the y. So there's an angle between them, and we could use some geometry to figure that out. But the easier way is to just use the shortcut, right? This is the dot product of 11 is equal to the product of the magnitudes times the cosine of theta. So what's the magnitude? Remember, magnitude is Pythagorean theorems. Be 3 squared plus 2 squared. So that's square root of 9 and 4. So square root of 13. And B vector would have a magnitude of 1 squared plus 4 squared, which would be the square root of 17. Okay, so that means this is equal to the square root of 13 times the square root of 17 cosine of theta, and all that's equal to 11. And so the cosine of theta is equal to 11 divided by the square root of 13 times the square root of 17. Okay, so with a calculator handy, we're going to do 11 divided by the square root of 13 times the square root of 17, which comes out to 0.74. And then we've got to take the inverse cosine of that, and we get an angle of 42.3 degrees. Okay, so that notation really comes in handy, because when we're talking about applying a force on an object, okay, and that force causes the object to slide through some displacement, and there's an angle of theta between them. Okay, we can completely generalize this statement by saying the work is equal to the force vector as a dot product with the displacement vector, which can also be shorthanded as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So you'll notice that that's the exact same expressions we started with. So the dot product is a very good representation of finding work. Okay? Now, when I say general, I'm saying that kind of loosely because all of those examples required F to be a constant force. So what if the force F varies? Over the displacement. Okay. Or maybe the displacement's not an entirely straight path. So as an example, imagine a particle, okay, that's being pushed along this path. Okay? Well, at every single instant, there is a force applied on it. Okay, so I don't know, so here's the force. We push on the object with this much force at that point. Now, it's only going to move along the path, which means a little bit of displacement here, a small straight line. So I can't use capital delta triangle x. We have to use a lowercase delta because it's a very tiny amount of displacement. Okay, and that would be true no matter where we are on this path. apply a force this way, that would cause a very tiny displacement in x. Okay, so then how do we find the work being done throughout this entire path? So what we want to do is every single one of these little pieces contributes a very tiny amount of work. Okay? So if I want to know the entire amount of work done, well, I have to take all these little pieces and add them up. Now, you'll remember from calculus that if I want to add up all these tiny little changes, that by definition is an integral. So we're going to do an integral of both sides, and this represents our most general form of work. Okay, so if we do an example, let's say force is an expression, say, we'll just say it's 2x. So as x increases, the force is constantly doubling based on its position. And we want to find the work done between x equals 1 meter and x equals 3 meters. So the work done would be an integral from 1 to 3. It's 1 meter to 3 meters. Okay, of our force function, which is 2x, over small changes in x. So remember, for integrals, we add 1 to the exponent and then divide by that number. And then we evaluate it at the limits. So this is going to be x squared evaluated from 1 meter to 3 meters. So when we plug this in, that's going to be 9, well, let me back up. That'll be 3 squared minus the lower limit squared. So 9 minus 1 gives us 8 joules of work.